We have focused in this course on how to deal with one variable observed for a time series. But what if you have two variables or even more? And so the purpose of this particular section is to discuss the basics of how to deal with more than one variable for a time series. And so what we're going to do is we're going to begin with essentially is the extension of an autocovariance function and an autocorrelation function to now having two variables at a time. And the corresponding functions are called the cross covariance function and the cross correlation function. So let's first take a look at the cross covariance function. We're going to have two variables observed over time, x of t and y sub t for t equal 1 to n. And what the cross covariance function is as follows. First of all, in terms of symbols, we're going to refer to it as gamma, subscript x and y to represent, well, what variables we're talking about. And then in parentheses, what time points are we talking about for that corresponding x and for the corresponding y. So the s is for x, the t is for y. And what is this? Well, simply a covariance for x of s and x of t. And so we would have the normal covariance formula associated with it, meaning that we have the expected value of x sub s times y sub t minus the expected value of x sub s times the expected value of y sub t. Okay, this then leads into a cross correlation function where we take that cross covariance function and we divide by what is actually the autocovariance function for x at lag s. At time s. We square root that. And then we also are dividing by the square root of the autocovariance function for y at time t. Okay. So now that we've defined the cross covariance function and the cross correlation function, now let's also look at an extension to the idea of stationarity that we've looked at before as well. So we're going to focus again on two different time series represented by x of t and y sub t, and we say they are jointly stationary in a weak manner, because we've talked about weakly stationary series for one series at a time. Now we're going to look at the weak aspect here with respect to two series. In order to be jointly stationary, both time series must have a constant mean. Both autocovariance functions must depend only on the lag difference. So these two basically represent weak stationarity for one time series at a time. And now here's the extension. The cross covariance function must depend only on the lag difference. Now, if we do have joint stationarity, then we can simplify our notation a little bit. So we're looking at the cross covariance function for x and y. Now we only have to look at the lag difference. So we have this h here. And it's very important that you understand, well, where is this h applied? This cross covariance function is a covariance. So we have the expected value of x sub t plus h. So notice the h corresponds to the first variable there, minus the mean times y sub t minus mu sub y as well. Now, the cross correlation function is defined as you might expect. It's rho sub xy, now in parentheses just h. That's the only thing that we have to worry about for the lag difference. Notice now how the autocovariance functions simplify in this expression as well in this setting. Okay, some notes here. First of all, the cross covariance function in this particular case where we're dealing with jointly stationary, that's also equal to the cross covariance function where notice how I have a y first here, and now I'm going backwards negative h lag. So let's actually write out what this would represent and why this makes sense for this to occur. So now we have y sub t minus h minus mu sub y times x sub t minus mu sub x. So notice, this is the most important part here, x sub t is still h time points ahead of where y is located. That's the key. The difference in how x is in relation to y in terms of the number of time points ahead or behind has to be exactly the same for this equality. Now, why this is all important is that when we have the cross covariance function as defined here, it is not necessarily equal, most likely it won't be, equal to the cross covariance function for y and x at this h. Let's take a look at what's happening here. Let me actually write it out. So we have expected value of y sub t plus h minus mu sub y, x sub t minus mu sub x. Notice now that y is h time points ahead of where x is. This matters. That's why we would have a different value. Now you might be worrying, well, we didn't have to worry about that when we were only dealing with one variable at a time. And the key is we were only dealing with one variable at a time. So when we had the autocovariance function, we would have a y right here. And it didn't matter because it was the same exact variable. It didn't matter. You were always either, this part was either always h time periods ahead or h time periods behind what you have here. But in the end, it was exactly the same variable. So you could reverse the, what you're talking about here. Now, since we have two different variables, this is why this matters. Also, the cross covariance function, as I originally defined, is not necessarily equal to the cross covariance function when we have a negative h there. So again, let's put that in, what this means. So the expected value of x sub t minus h minus mu x, y sub t minus mu y here. Now we see that y is h time points ahead, where before x was h time points ahead. Since they're different variables, now it matters that this aspect now matters. Okay, so let's take a look at an example. This example comes from Shumway and Stouffer's book, and we've actually previously looked at part of this example. We're going to let x sub t be equal to wt plus wt minus 1. We're going to let y sub t be equal to wt minus wt minus 1. Wt is going to be independent white noise. Now, what we showed earlier was that x sub t and y sub t were weakly stationary themselves. Now what I would like to be able to do is show that they are actually jointly weakly stationary too. Okay, so to do this, we need to take a look at our cross covariance function. So this is what it looks like. Now, both of the means of the series are equal to 0, and you can see if I were just simply to take an expected value here, we see that we have the expected value of wt plus wt minus 1. Each of those are independent, mean of 0. So that's why expected value t is 0, and a similar thing for y sub t. Okay, so this all simplifies down to the expected value of x sub s, y sub t. Let's plug in what x sub s is and what y sub t is as well. Then let's multiply out all the terms within inside the expected value. So what I do here is I first take this wt, multiply it by ws, take this wt, multiply it by ws minus 1, and this is what I get. And then I do the same thing with w sub t minus 1. Okay, so now we're left with a situation that we've seen many times before, where I have to look at various situations of is s equal to t, is s equal to t minus 1, and so on. So let's go ahead and do this. So let's say that s is equal to t. I'm going to find this cross covariance function. So that means wherever I see a s, I'm going to replace it with a t. And so that's what I do there, and so on. Okay, now we can move the expectation through the sum. And remember, each of the w's are independent of one another, so that if the two subscripts are different, that means I can bring the expectation with inside the sum. So for this part here, I would take expected value of wt minus 1 times wt itself, which is equal to the expected value of wt minus 1 times expected value of wt. Each of these expected values are 0. So the only time that I need to worry about having a non-zero value is when the subscripts actually match up. Okay, so then I'm left with expected value of wt squared minus expected value of wt minus 1. That w is squared. Let's rewrite this in terms of the variance plus expected value wt quantity squared. I do the same thing for wt minus 1 there. Again, these become zeros. I'm left with two variances. Both of them are exactly the same, sigma squared w. So look at this. This is kind of interesting. The cross covariance function, when the time indices are the same, is equal to 0. Okay, let's move on. Suppose s is equal to t minus 1. So again, wherever I saw an s before, I'm going to replace it with a t minus 1. Once again, the only place that we need to worry about here in terms of having non-zero values is when the subscripts match up. And it only occurs for this situation in one place. So I'm left with a negative expected value of wt minus 1. Work with the variance, and you get negative sigma squared w. If s is equal to t minus 1, I can do the same thing. In the end, I only have one set of w's that have subscripts that match up, expected value wt squared, and I'm left with a positive sigma squared w here. Well, what happens though if the difference between s and t in terms of absolute value is greater than 1? Let's go back up to what we originally had here. And let me do a little bit of erasing as well. If this difference is more than 1 in absolute value, I'm not going to have any of these subscripts match up at all. And so because of that, then, this corresponding cross covariance is always going to be equal to 0. So in summary, this is what I have. Lag equals 0, have a value of 0. Lag equal 1, or positive 1, sigma squared w. Lag of negative 1, I have negative sigma squared w. And anything greater than 1 in terms of absolute value, I have a 0. So we see that this cross covariance function is not dependent upon s and t, only on the lag difference. So therefore now, combined with the previous work that we had done, x and t are jointly stationary in a weak manner. Okay, let's take a look at one more example relative to this. Here we have the usual autoregressive one model that we've seen in this course. Wt is distributed independent mean 0, variance sigma squared w. And let's look at this a little bit a different way. Is x of t and w sub t jointly stationary? Okay. Previously, we have seen x of t to be stationary if this is true. Wt itself, of course, would be jointly, okay, let me make sure I said this right. We've seen that x of t itself is weakly stationary before. Wt is going to be weakly stationary too. I mean, look at this. It's independent, mean 0, variance sigma squared w. So, you know, the autocovariances are not going to change at all as a function of t. So, let's look at jointly stationary now. let's rewrite our model so that we have moved this 1 over 1 minus phi 1b to the right-hand side of the equation. Then we know we could simply write this out in terms of an infinite order moving average. We went through this kind of derivation before, and you can quickly see why we can use these particular terms in the infinite order moving average by taking a look at the sum of an infinite series. Okay, now let's look at the cross covariance function. So notice x is first. So I have x of t plus h minus the mean of x at time t plus h times the quantity wt minus the mean of w at time t. Of course, this is 0, and that is going to be 0 as well. So we have a nice simplification here. With this cross covariance function, let's actually write everything out in terms of the w's. So what I'm going to do is replace x of t plus h with what it is in terms of that infinite order moving average model. Then I'm going to multiply out each of the terms by this wt. Okay. Now, as we've seen in the past, each of these w's are independent. So the only time that we're going to have a non-zero value for this expectation is when the subscripts actually match up. So let's take a look at an h equals 0 here. When I have a 0 in there, look what happens. I only have the expected value of wt squared. Excuse me. What happens if I have a 1 in there instead? Then look at when that matches up right there. So that will be my only non-zero term here. And I'm left with phi 1 times wt, phi 1 times expected value wt squared. So now I get phi 1 times sigma squared w. What if, though, if I have a negative 1 in there instead? So I go down one time period. Then look what happens. None of these subscripts match up at all, and I'm left with a value of 0. So in general, one can keep on going for more positive values of h and find the cross covariance function to be sigma 1 raised to the h power times sigma squared w for h greater than or equal to 0. When h is less than 0, I get a cross covariance of 0. And hopefully this makes some intuitive sense, because, where does x of t minus 1 come from? Well, it comes from knowing these past w values. What x of t minus 1 is has no bearing on what wt is. And so that's why it makes some sense then for these cross covariances to be 0 in these particular kinds of cases. So therefore, x of t and wt are jointly stationary. Next, let's look at how we can estimate the cross covariance function and the cross correlation function for a jointly stationary set of two time series. So the estimated or the sample cross covariance function is approached in a way that you normally would expect. First of all, in terms of symbols here, I have a hat on top of the gamma to represent that this is an estimated quantity. And then I'm going to take 1 over n so I can get kind of an average value of the sum t equal 1 to n minus h. And I take x of t plus h minus the corresponding sample mean, and take yt minus its corresponding sample mean as well. That's the sample cross covariance function. Similar to what we've talked about before with the true cross covariance function, we have certain values that will always be equal to one another, but then we have other representations that, if you're not careful, you have to realize that most likely will not be equal to one another. Please make sure you understand why now relative to the estimated versus the true one that we talked about previously. Then the sample or estimated cross-covariance, cross-correlation functions denoted by rho hat sub xy and then in parentheses h for the lag difference. And as you might expect, it's exactly the same as the true cross-covariance function as we saw before, but now I put hats on top of the corresponding unknown values. Well, what about the variability that we would expect from one sample to the next? That's where the sampling distribution comes in for the cross-correlation function. This distribution is approximately normal with a mean of 0 and a standard deviation of 1 over square root of n if the sample size is large and at least one of the series is white noise. So this is very similar to what we saw before with the autocorrelation function when we were looking at a sampling distribution for that. This is just the direct extension. So what this then is going to give us then, similar to again what we saw with the estimated ACF, we can look to see is the estimated cross-correlation within plus or minus the 1 minus alpha divided by 2 quantile from the standard normal divided by square root of n. If it's outside of that range for a particular h, that says that we have a significant value, meaning we do have sufficient evidence to indicate the cross-correlation does not equal 0. However, if this estimated cross-correlation is inside this range, then we don't have sufficient evidence to indicate that indeed that the value was different from 0. Okay, so let's take a look at an example. This is a simple CCF example. CCF stands for cross-correlation function. Now, in this particular example, I show you how to do this stuff in R, but also I have this Excel spreadsheet set up so you can see how some of these by hand calculations are done. I found that this was necessary to do to fully understand how R was doing some of its calculations. As you will see shortly, how R actually labels stuff can be confusing, and so this is how I was able to figure out what R was actually doing. So in this Excel file here, I have my sample. I have some X and Y. I only have 6 different data values. At time 1, X sub 1 is equal to 1, and Y sub 1 is equal to 2. And so what I have laid out here is for different h's, let me actually page on over, h equals 0 to 3, and then also I do h equal to -1 as well. What I do here is I have what the estimated cross-covariance function calculations would be. So let's take a look at for h equal 1. That would mean I need to take x of t plus 1 minus x bar, and then multiply by y sub t minus y bar. And we can see this here if we actually go into the corresponding formula in Excel. So x of t plus 1 would be the time point, if you see where my mouse is, time point 2. So I would need x sub 2, which it happens to be 2. And then I subtract off the mean, which happens to be 3.5. So this is actually a formula here that does equal average over all the x's. And then I take that times y sub t, or I'm sorry, y sub 1, which would be 2, minus the corresponding mean, 4.67. And what do I get? 4.0. And I do this all the way up to time point 5. Now, notice I cannot do it for time point 6 because I would actually need an x of 7 to do this calculation, which I don't have. So when I sum up these corresponding values, I get an estimated cross-covariance value of 2.556. Okay. So let me come back over here to my Word document. And this is the one calculation that we just went through. The cross-covariance function at lag 0 is 2.167. Using this information then, I can find the corresponding cross-covariance function. So at lag 1 here, there's the 2.556. I can also find the autocovariance for x, the autocovariance for y. My Excel file does not go through the, let's say, the by hand calculations for that. All I do is I rely on calculations that are given in R to find those particular ones, which we have actually seen before. So for example, here is gamma hat sub x, and then it's at lag 0. So that 2.917 goes right in there. I get a cross correlation value estimated to be 0.758 at a positive 1 lag. Okay. So let's talk about how we can do this in R. There's actually two different functions that allow us to do these kinds of calculations. The first one is a familiar function to us already. It's called ACF. And with ACF, similar to what we've seen before, I have a type argument, and if I put covariance there, now that's going to give us the cross covariance function values. And now since I have two different time series here that I'm interested in, I'm going to combine by column using the cbind function x and y. So this is simply going to create a matrix that has all the x values in the first column and all the y values in the second column, if by chance you haven't seen the cbind function before. And I put this into the argument x. What's going to happen is that R is going to produce a plot of the corresponding cross covariances and also the autocovariances for x and also for y. So it's actually going to produce 4 plots in one plotting window. If I were to simply print off the results from this object where I've saved in the corresponding calculations in, this is what I get. So first of all, we get the autocovariances for just x itself. And what we have here is our h. That's what's in parentheses there. Why is it in parentheses? Well, we typically put it in parentheses, I guess, with our corresponding notation for an autocovariance function. Then, and also let me emphasize, notice we have an x here, we have an x here as well. The way that R is storing this stuff is in an array kind of format where you can think of it like the strata as being the corresponding first letter. So you could actually put gamma of xx there. Okay, next, this second column corresponds to gamma hat sub xy parentheses h, where h is always less than or equal to -0 here. So again, here's h. So what that means then is gamma hat xy for -1 is equal to 0.61. Now I've actually went through that calculation in my Excel spreadsheet. So if I page all the way over, there it is located right there to confirm what this actual value would be. And let me actually make one little change here in my, no, actually that's right, excuse me. That labeling is correct because I'm taking x of t now minus 1 because h is -1 there. Okay. Next, let's actually go right below it. And what we have here is the autocovariance function for y. Notice now here in this labeling we have a y. We have a y there as well. So this is the estimated autocovariance function for just y. And then lastly here, what we have is as follows. Notice how I have a y first, I have an x second. So what we could do is put a y first there in terms of our notation, an x second there as well. And if we assume that we have a negative out in front of h, so that when I have a 1 here, that means I have a -1, then this is equal to gamma hat y x -1, which is 2.56. Okay, now because of the relationships that we saw earlier in terms of the equivalences, go back to the actual equation, write it in terms of a covariance, write it in terms of the expected value so that you make sure you understand what's going on here. This value is also equivalent to having gamma hat x, y positive 1. 2.56, which corresponded to this, actually let me just come over here to the spreadsheet, corresponded to this particular value that we were originally going through the calculation with. So that's how this notation is set up here. It obviously can be a little bit confusing. My recommendation to you is one can always think of this, the results here, as being displayed as to always think of as x coming first with respect to the cross covariances. So that, notice, think of where you see my mouse is. Let me actually get a pen out. So this part here in gray, think of that instead as gamma hat sub x, y, and then here is my h. Also, this one's a little bit easier. Think of this as, again, as gamma hat of xy, but now I have a negative h in there instead. Okay, so let's move on. Now, to calculate then the corresponding cross correlations, I just replace the type argument. Instead of having a covariance there, now I have a correlation. And here is the corresponding results. So for example, right here, gamma hat xy negative 1 is 0.181. And then right here, oops, that should be a row, excuse me. Rho hat xy positive 1 is 0.759, which again corresponds to, let me just go back up here for emphasis, corresponds to this right here. I have 0.758 just because there's some rounding error rather than 0.759. Okay. Every time that you run this particular function, you're going to get then the corresponding plot. And that should have a hat on it. And that should have a hat on it as well. Now, this first plot here is the estimated autocorrelations for x. The plot in the 2, 2 position, row 2, column 2, is the autocorrelation plot for y. Now, here's where things are also confusing with respect to how R is doing this. Okay, notice how we have positive lags for this plot that's in the row 1, column 2 part of this 2 by 2 plotting area. What's actually being plotted here is rho hat sub xy of h. Notice, for example, that cross correlation is 0.758. So in row 1, column 2 corresponds to what was actually in, if you think of these as rows and columns, row 2, column 1 of the corresponding output from the ACF function. And similarly, what we have here in the row 2, column 1 output, notice how we have negative lags here. This is rho hat sub xy of h, now for negative values. So negative h value. So for example, I believe that value is positive 0.181. Let's go back to our output to find that. And there we go. I already had it circled. 0.181. So anyway, so it appears basically that R kind of transposes what was in what would be in the R console in terms of its output, transposes that for its corresponding plot. It's kind of disappointing that R does that, but that's just what you have to get used to. Now there's also another function that can be used to do these cross correlations. There is a CCF function where the first argument corresponds to your first variable of interest, and in our case is going to be x. The second argument corresponds to the second variable of interest. In our case, it will be y. If I say type equal correlation here, this is what we get. So for example, here is rho hat xy for 1. Here is rho hat xy for -1. R then also produces a plot of the corresponding cross correlations as well. Okay. So let's move on to an actual data example. This example corresponds to something that's in Shumway and Stouffer's book. The authors are interested in this El Nino phenomenon, or La Nina as well, relative to the fish population. And so what the authors do is that they have these measurements of the Southern Oscillation Index. We're going to call that X of T. And it's a measurement of the air pressure in the Central Pacific Ocean. And what this index helps one do is to determine when there is an El Nino or La Nina effect present. Obviously, air pressure corresponds to temperatures as well, and so I believe this is why the authors are focusing on this. Also, they have another variable which they call recruitment. I'm going to refer to this as y sub t, and that's the number of new fish. I'm not necessarily certain how they're doing this count. We'll just let them present then this corresponding data here for how the fish count comes about. And in the data set, there are 453 months, so we have monthly observations. The data is in two different time series class objects in R, SOI for the air pressure, and REC for the recruitment, the number of fish. The data is in their corresponding package, ASTSA, and there's just showing that indeed that is a TS class object. With TS class objects, especially when you have a long time series such as what we have here, often it's helpful to use the window function to only look at part of the corresponding time series. So if I only want to look at let's say 1960 in the time series, I can do that by saying window x argument SOI. I'm going to start in 1960 and end right before I get to 1961 so that I can see from January to December what the Southern Oscillation Index values were for the time series. Here's also how you could do the same thing for the year 1980. If I actually did go up to 1981 rather than saying 1980.99, look what happens. I do get January of 1981. So let's do a plot of the corresponding time series. So I'm going to first plot the SOI. Notice I'm using type equals O there, which corresponds to I want both lines and dots plotted. In order for the grid lines to line up properly with the corresponding y-axis and x-axis tick marks, I cannot use the panel.first argument with this, and so instead I use the grid function outside of calling plot, and this lines everything up nicely. And here's what we get for this particular time series. Obviously, we see some up and down behavior in this particular time series. We can also do this kind of plot for the recruitment in terms of the number of fish, and we also see some kinds of patterns here. Now, for those of you who are not familiar with El Nino, La Nina, there is a particular pattern that's typically happens, kind of like what we saw with the sunspots and previously in the course, where I think it's about every 3 years up to maybe every about 5 years or so, where we see a pattern of we have an El Nino year, let's say maybe every 5 years and so on. Okay, so now let's do the estimated cross correlations. The estimated cross correlations, excuse me. I'm going to put the results into an object called soi.rec.acf. And so to do this, I need to combine together the two different time series. I'm going to go up to a lag of 50. The reason why I'm going up so high here is because we actually have some seasonal aspects to this, because as I mentioned just about a minute ago, the El Nino effect maybe occurs about every 5 years. And so here's the corresponding output. I've also put in the corresponding labels here to help remind you what each of the parts, at least the cross correlation parts, represent for our particular time series. Again, X is going to be for SOI. Y is going to be for recruitment as well. Now, in terms of the lags that we see here, what R does, it takes into account that this is monthly data. And so this, what we normally would think of as this, well, this is lag 1, H equal 1 here. But what this represents is essentially 1/12 of the year. Here we have 2/12 of the year, and that's just how R is doing the labeling for the lags instead of using the traditional H equal 1, H equal 2, and so on. And so what we do see is that, look at it, we are starting to get a kind of a large negative correlation here. Do note that I've edited the output. The reason being is because since I use such a large number of lags, we actually get 50 of these values listed there and also 50 listed here. I didn't want to show them all because we can actually look at a plot. And this is what we see. So we definitely have some seasonality with these cross correlations and even the auto correlations as well here. We see this pattern that seems to be occurring. So what's interesting is this right here. Okay, so what this is representing then for us is that when that air pressure is, let's say at high levels, I have a negative relationship with the number of fish. And it's delayed a little bit for when this occurs. And we also have that opposite effect too, that when I have a, let's say, low pressure, I tend to have a higher number of fish. And we can see how much it's delayed by looking at the corresponding lag difference. Here's then the corresponding plot as well using the CCF function, and this is what I was pointing out before. Okay. So that gives you some information then of dealing with two time series at a time. What happens if you have more? Well, you can extend the same kinds of ideas regarding this too. So I could have a vector of these different time series. I could have, let's say, up to p different time series in total. And this would be let's say, the observed values or the random variables too at time t. From that then I could have a mean vector as well, an autocovariance matrix that looks at the dependence between all the different time points and so on. And with this autocovariance matrix, even though I call it autocovariance matrix, you're going to have cross covariance as well. So here's the cross covariance between, let's say, the first xt variable and the first variable corresponding to x and the second variable corresponding to x as well. You could calculate sample or estimated autocovariance functions as much as you would expect. I'm not going to go through all the details, so looking at this in terms of 3 or more time series variables. If sometimes in a course like this, I will take a look at extra stuff that you can do with it. And if I do in this particular class or this particular semester that I'm offering this course, then we'll look at this more in more detail. But I just at least wanted to tell you that it is possible to work with more than 2 time series at a time. And this is some of the very basics behind this. But unless we have another section on this specific topic, you would not be responsible for this on a test. And one last thing I want to end with too is that, here we're looking at, excuse me, we always have one index, time. But you could also index, let's say, a particular variable by maybe 2 values, or I guess even 3. But in terms of, let's say, 2, you could index by, let's say, longitude and latitude. And you could do similar things to what we've essentially done here as well, and looking at ways to measure dependence and stuff. Looking at more than one index is beyond the scope of the course. If you're interested in learning how to do that kind of stuff, take a course on spatial statistics. So spatial, you're looking at things in space, you could say. So looking at longitude and latitude indexes would correspond to that kind of an aspect. So that concludes then this particular section on how to deal with more than one time series at a time.